idempotent law, associative, commutative law. Okay, based on only one single preposition. Preposition P with intersection of T, result is T. Preposition P intersection of F, result is F. So preposition P union T equal to T. Preposition P union F equal to P. So depends on P values. P got a different equivalence relations. And of course, we discussed one proof also. Let me do some more examples on same that equivalence relations with the help of that all 11 principles. Okay, let me discuss few examples on that. Okay, I will share the screen. So I will explain the one problem both in both cases, with truth tables and without truth tables. Okay. See here. So these are the principles we discussed in a previous class. Based on all these associative property, idempotent law, commutative law, distributive law, absorption and De Morgan's, and this converse, inverse, and contrapositive. Okay, let me do few examples. Last class I finished this problem. Let me do one more. So show that second example. Show that negation of P implies Q. It is equivalence to P intersection negation of Q. Okay. So what we have to prove? Negation of P implies Q. It is equivalence to P intersection negation of Q. So let me take first LHS part as negation of P implies Q. Actually, what is P implies Q formula? As P implies Q is it is negation of P union Q. If you convert this P implies Q, as previous class I explained the formulas also here. Here we have. Here, negation of P implies Q. Negation of P implies Q is negation P union Q. So if you convert this implies conditional formula in terms of disjunction, it will become P implies Q equal to negation P union Q. So just I am applying the principle for inner function, not P implies Q. So I am writing negation as it is. Negation of P implies Q will become negation P union Q. Okay. So this is again, if you apply the negation principles, what about negation of P union Q? So apply the De Morgan properties. So negation of negation P intersection negation Q. So negation of negation P will become P. So P intersection negation Q. So for proving this result, I am using two principles simultaneously. So negation of P implies Q. What we have to prove? It implies P intersection negation of Q. So for proving this result, here, this is, I'll show it. Negation of right. Negation of P implies Q equal to negation of P intersection Q. This is we have to prove. This is question. Now for proving this, come to the proof. So here I am using two principles. What is first one? P implies Q, it is equivalence to, this is negation P union Q. This is first principle I am using. So if you convert this P implies Q, it is equal to negation P union Q. So again, I am taking one more principle, that is De Morgan laws. Negation of P union Q will become De Morgan property. Union will become intersection. So this is negation of P intersection negation of Q. So this is a conditional principle and this is De Morgan principle. So by using these two principles, I am proving this result without constructing truth table. See here, what is the LHS part here? The LHS part is negation of P implies Q. Okay, negation of P implies Q. This is equal to, first I'm writing it is equivalent to negation of so write P implies Q equal to this first principle, negation P union Q, negation P union Q. So I got this is negation of P union Q. It implies for both this negation P union Q, apply De Morgan principle. What is negation of P union Q formula? If you apply the De Morgan property for union, negation of P union Q will become negation P, union will become intersection negation Q. But here we have, in the place of P, compare this, in the place of P here we have negation P, already it is negation. And in the place of Q, we have Q itself. So if you apply the De Morgan principle for this one, it will become negation of negation P, union will become intersection negation of Q. What is negation of negation P? It will become P. So P intersection negation Q. So this is we have to prove. Yes, we got the result. LHS equal to RHS. Okay. So negation of P implies Q equal to P intersection negation Q. Now this result, I am proving this result with construction of truth table. So in this, I didn't use any truth tables. For this problem, if you use the truth table, we will get the same result here. Okay. What is the LHS and RHS will become same quantity. As next here, one more question. Yes. I'll share the screen. Here, one more example. Yes. Prove that. Third one. Show that P implies Q intersection R implies Q. It is equivalence to P union R implies Q. So in this, I am going to take three prepositions simultaneously. We have preposition P, preposition Q, preposition R. Among these three prepositions, what we have to prove? The result is P implies Q intersection R implies Q. It is equivalence to P union R implies Q. So first let me take LHS part. So whatever the proofs we are going to prove that quantity, please remember these principles, because without these equivalence relations I can't prove. We can't move single step also. So all these principles, yesterday I explained this, around 7 principles or 11 principles are there. Among these, by using these 11 principles, you can prove any one of the equivalence conditions. So first coming to this problem 3. So show that P implies Q intersection P R implies Q, which is equivalence to P union R implies Q. So what is the LHS part? P implies Q intersection R implies Q. So first apply the P conditional Q formula. If you convert this into union, P implies Q will become Just now in previous case also we used this formula. What is P implies Q? Negation P union Q. Okay, negation P union Q intersection. Second one, R implies Q is there. R implies Q means again apply the P implies Q formula. But in the place of P, here we have R. In the place of Q, we have Q itself. So it will become negation R union Q. See here. First, I applied the first principle. Negation P implies Q will become negation P union Q. And R implies Q will become negation R union Q. Okay. Next, it implies, again see here, apply the distributive properties. Yes, I written here which formula we are using for getting the result. So in this, I am using distributive formula for this. So what about distributive formulas? We have two distributive formulas. A, see here, this sports formula. P union Q intersection R equal to P union Q intersection P union R, or P intersection Q union R equal to P intersection Q union P intersection R. So in this here, in the question we got this right side quantity P union Q intersection P union R. Write this into in terms of P union of Q intersection R. So I am using this fourth distributive formula, first case, first one. See here. So distributive, if you apply the distributive formula, it will become negation P is union Q intersection negation R union Q. So I am taking Q common here, it will become negation P intersection negation R union of Q. This is right distributive law. Okay, right distributive law. So again, if you apply to this, we can get the negation P union Q intersection negation R union Q. Next, see here. After this, negation P intersection negation R is there. So apply the De Morgan laws among this P and Q only. So if we take negation outside of this, intersection will become union. So negation of P intersection negation of R will become negation of P union R, union of Q. Again see here, yes, P implies Q. What is the formula for P implies Q? Negation P union Q. So same this principle if you apply for this one also. Negation of P union R union Q is there. So here assume P union Q is the complete one single proportion, so single preposition. So assume P union Q, sorry, P union R is the only one single preposition. So it is in the form of negation P union Q. Negation P union Q can be written as P implies Q. But in the place of P, we have P union R. So negation P union R union Q will become, it is equivalent to P union R implies Q. Okay, this is here, I written formula here. So by using this one, we can put the results. Okay, let us take some more example. Yes, show that P implies Q union R. It is equivalent to P implies Q union P implies R. Okay, P implies Q union P implies R. So let me take LHS part. P implies Q union R. Every time this is the basic formulas here. Is it clear? I'm using this one. P implies Q equal to P implies Q equal to equivalence to what is P implies Q? Negation P union Q. Okay. Whatever it may be in the place of P, whether it may be depends on the question or in the place of Q, whatever it may be. But every time use P implies Q equal to negation P union Q. Again, for in this result also, I am going to use this principle. So what about formula? P implies Q union R. For this quantity, I am applying the P implies Q formula. In the place of P, we have P itself, but in the place of Q, we have Q union R. So it implies P implies Q union R will become negation P union Q union R. Okay. Next, see here. For this, apply the negation P quantity. So this is negation P union Q union negation P union R will become, this is P implies Q union P implies R. So this is negation P union Q union of negation P union R. So negation P union Q means, again I apply the reverse strategy. This is negation P union Q. What is this formula? It is equivalence to P implies Q. So this is negation P union Q means it is P implies Q. Negation P union R will become P implies R. This is the result. Okay. So these are the few logical equivalence relations. Let us do one more example. Yes, here. As for final exam purpose, for long answer purpose, please refer the these type of questions. Please prepare the this type of questions here. So fifth and sixth. After finishing these two, I will move the next topic. Here. Prove that or show that negation P implies Q, which is equivalence to P implies Q implies P. P implies Q implies P. Or again it is equivalence to totally it is true. Means it will goes to tautology. Yes, yesterday I explained three definitions. Tautology, contradiction, contingency. Yes, what is the these three definitions? What it refers? Tautology means tautology. What is the meaning of tautology? The entire quantity having only the truth value having true only. It consists all true, then it is comes under the tautology. Next, if it is contradiction means the entire truth table final quantity will become only false conditions. Okay, then it is contradiction. If contingency means a preposition is said to be contingency if it is neither tautology nor contradiction. Means it consists some of the values are true, some of the values are false statements. It is a combination of true and false is there. Then that kind of prepositions are known as contingency. So in this example is asking prove the equivalence relation. Finally is asking prove that it is a T. Means it will goes to all column values, last column values of the given question will goes to true values only. It means tautology. Okay. Yes. Here. Let me discuss how we are going to prove this one. I'll show it. Here. It's asking prove that this is first statement is prove that negation P implies Q. It is equivalence to P implies Q implies P, or it is equivalence to T. T means the entire column values will goes to true only. Means simply we can show that it is an example of tautology preposition. See here, coming to the first negation of P implies LHS part. Negation of P implies Q will become yes. Negation of P I am writing as it is implies what is P implies Q formula? Negation P union Q. Yes, I am applying the formula for second one. So negation P implies Q will become negation of P, which implies P implies Q will become negation P union Q. Again, here apply the negation P implies negation P union Q. For this, again apply the P implies Q formula. In the place of P, here we have negation P. In the place of Q, here we have negation P union Q. So P implies Q will become negation P union Q. So already in the place of P we have negation P. So it will become, after applying the formula, it will become negation of negation P union Q. Okay. Next, negation of negation P will become P union P union Q. Okay. Just I am applying the associative principle. P union negation P union Q. Just I am changing the brackets. That is associative principle. A union of B union C is always equal to A union B union of C. So P union negation of P implies Q can be written as P union negation P union Q. Okay. What is P union negation P? It's already explained this principle yesterday. P union negation P will become, that is always true. Okay. True union Q. What is P? The true value with any preposition, always it is true only because it is union condition. In union, any one of the statement is true, then resultant vector is true. When it is false, the both situations will go to false. In that case only it will go to false. But remaining three cases, TT, TF, FT, always it shows union will shows true only. So we got this. Okay, is it clear? T union Q equal to 2. Yes, I proved negation of P implies Q equal to true. Similarly, let us take LHS part. What is LHS? Sorry, RHS part. Let us take now. Just now we proved with LHS part. It is 2. Next, take RHS part. What is RHS value? P implies Q implies P. It is equal to true. Okay, coming to this. P implies Q implies P, which is equal to, first apply the P implies Q formula for Q implies P. So I am writing P implies as it is, P implies as it is. Q implies P means negation P union Q. So, but in the place of P we have Q. In the place of Q we have P. It is interchanges here. It is not P to Q. It is Q to P is there. So Q implies P will become negation Q union P. Right. Next, it implies, again apply the P implies Q principle for P implies negation Q union P. In the place of P, here we have P itself, and in the place of Q we have negation Q union P. So again apply the one more time that same principle. P implies Q equal to negation P union Q. So it is negation P union of negation Q union P. Okay. Next, negation P union. Yes, I'm using that commutative property. A union B is always equal to B union A. So I'm writing here negation Q union P is always equal to P union negation Q. After this, again go for the associative principle. A union of B union C will become A union B of union C. So apply that principle. It will become negation P union negation Q. So what is negation P union P? Yes, it is always true. True union of negation Q. So true with any preposition union. I am applying the union disjunction condition. So if it is true, union of irrespective of any preposition, the result is always true only. So this is true. So I proved LHS quantity tends to true. RHS quantity is also tends to true. These are the some different examples. Of course, all these problems are I have taken from your textbook only. Okay, and I referred a few question papers also. See here. Next question. This is also important. Just listen. Show that negation P union negation Q intersection R union of Q intersection R union P intersection R. It is equivalent to the entire this function will be goes to the preposition R only to prove that it is R. Okay. So see here. Negation P. I'm taking first LHS part. Negation P intersection is negation P intersection negation Q intersection R. So it can be written as negation P intersection negation Q intersection R. It can be written as, sorry, union of, what about when we have one more function, union of Q intersection R union P intersection R. So it implies negation P intersection negation Q. Just in this, I am using the associative property. A intersection of B intersection C can be written as A intersection B of intersection C. Just I am applying the associative principle here. So it implies negation P intersection negation Q, and extra we have or intersection or. I'm writing as it is. Union, come to the second union, Q intersection R, union P intersection R. In between these two, apply the distributive property. A intersection B union B intersection C. Yes, listen. A intersection B union B intersection B can be written as A union B of intersection C. This is the distributive. Right distributive law. So I'm applying the right distributive law for this. Right. Right distributive law here. So this is after distributive law. We got like this. Next. Next here. This is negation P intersection negation Q intersection R union of Q union P intersection R. Next, negation P intersection negation Q. Apply the De Morgan property in between P and Q because we have negation P intersection negation Q. If you apply the De Morgan property, it will become negation of P union Q. Negation of P union Q and write intersection R as it is. Intersection R union of Q union P intersection R. Next, in between these two, next step, I'm writing negation P union Q union P union Q intersection of R. Why? Because here we have in first function P union Q intersection R union Q intersection P. Q intersection P, can I write it is Q intersection P equal to P intersection, sorry, Q union P is always same as P union Q. That is commutative property. A union B always equal to B union A. So Q union P, I'm going to write P union Q. So then both functions having the same quantities here. Negation P union Q intersection R union P intersection Q, P union Q intersection R. So I can apply the distributive properties. A union B intersection C. So in the place of A, here we have P union Q. In the place of B, we have Q union P. In the place of C, we have R. Yes, I will repeat once again. Here I am applying the right distributive law. In the place of A, I have negation of P union Q. In the place of B, I have Q union P. Again, in the place of C, I have R. So A intersection B union A intersection C is always equal to A union B of intersection C. So this is negation P union Q union of P union Q intersection R. Again, here the functions are same here. P negation P union negation Q. What is negation P union negation P union negation P union P value? It is always true. Yes, I will show it the one of the principle. Here, I am using this principle. Yes, is it here? Here. Ninth first formula. P union negation P is always true. P union negation P is always true. But in the place of P, here I have P union Q. In this formula, in this problems here. In the place of P, here we have P union Q. So negation P union P is always true. So this total quantity will goes to true. T intersection R. T intersection R is always that corresponding same preposition. So what is their preposition R? So T intersection R is always R. Just I will show that principle also here. Here. P intersection, where it is S, here. Seventh first formula. P intersection T is always P. So you can apply the intersection property to any preposition with combination of true. It is always same preposition. If it is P unta P or Q. Okay. So this is the result. It is totally will become R quantity. This is always equal to R. Similarly, let me discuss this. All these are the different examples. Okay. Next year. Yes. Let me do one more because all these are just for long answer purpose. There is a scope to ask this kind of questions in your final exam. So let's show that negation of P implies Q. Negation of P implies, sorry, it is not implies, it is biconditional, double implies. Negation of P double implies Q. It is equivalence to P intersection negation Q union negation P intersection Q. Okay, this is we have to prove. Yes, what about our question? Negation of P double implies Q, that is biconditional Q. It is equivalence to P intersection negation Q union negation P intersection Q. Again, coming to the first LHS part. What is LHS part? Negation of P biconditional Q. It is negation of P implies Q is there. So first, let me convert that biconditional properties into conditional property. What about biconditional property? P double implies Q is always equal to, in terms of intersection, it is always equal to P implies Q intersection Q implies P. Okay, it's the one of the principle which we discussed in last class, right? So here I written here P double implies Q is always equal to P implies Q intersection Q implies P. Okay, but in front of this preposition we have uh, negation notation. So negation of P W implies Q will become negation of P implies Q intersection Q implies P. Next, it is equivalence to negation of, again, what is P implies Q again? Conditional principle in terms of union. P implies Q. So we used this principle in previous results also. Negation P implies Q equal to negation P union Q. Okay, but already outside we have one negation. Negation of negation P union Q intersection. Again, Q implies P means, what is Q implies P formula? Negation Q union P. So negation of negation P union Q intersection, negation Q union P. Next, now apply the De Morgan principle. De Morgan of principle of, that is negation of P intersection Q will become negation P union negation Q. Intersection will become union, union will become intersection. So negation of P intersection Q is always equal to negation P union negation Q. But here in the place of P, I have negation P union Q. In the place of Q, that is second preposition, we have the combination of negation Q union P. So if you apply the De Morgan principle for this, it will become negation of negation P union Q intersection negation Q union P will become negation of P, means negation of negation P union Q, and intersection, this intersection will become union. Union of negation of Q means, what is Q here? Negation of negation Q union P. Again, apply the De Morgan principle for this. Negation of negation P union Q will become negation of negation P intersection negation Q. But what is negation of negation P? It will become P only. So P intersection negation Q union. Second one, again apply the De Morgan principle for this. Negation of negation Q union P will become negation of negation Q intersection negation Q. But what is negation of negation Q? It is Q only. So totally we got finally P intersection negation Q union Q intersection negation. That is we have to. Okay. Next, one more example. All these are the practice problems. Please do these problems by yourself. Just I will explain this here. Show that, what about result? Negation of P double implies Q. Here same above result only. But we can get this in terms of another manner also. So here, what is the difference between these example 7, example 8? Example 7 is show that negation of P implies Q, PW implies Q equal to, it is answer is product of sums. Union will become sum, intersection means product. So all products I am adding P intersection 7Q and P intersection negation Q and negation P intersection Q. I'm taking two products. I'm adding these two products with union. That is P intersection negation Q, union negation P intersection Q. So negation P W implies Q formula in terms of product of sums. If you convert same this into sum of products, say this is same question. Negation of P W implies Q equal to. So here first I am adding P union Q. Next I am adding here negation of P. This is P intersection Q. This is P intersection Q, and this is equal to the combination of this is intersection quantity. P it is not sorry sum of the products. It is first combination is P union Q intersection negation P intersection Q. Let me do this problem by step. See here. First LHS part. What is LHS part here? Yes. Negation P double implies Q, which is equivalence to S, which is equivalence to what about result? P implies Q intersection negation P intersection Q. This is I want to prove. So I am writing this first LHS part. Negation of negation P implies Q. Negation of negation P implies Q, which is equals to. Yes, what is P double implies Q? Biconditional formula. Yes, just now we used it in previous case here. P double implies Q is P implies Q intersection Q implies P. Okay, this is the double implies in terms of intersection part and conditional principle. So I am writing same step here. Negation of P implies Q. It implies negation of first P W implies Q can be written as P implies Q intersection Q implies P. Okay. Next negation of again what is negation? Again what is P implies Q? Conditional property P implies Q is negation P union Q. Negation P union Q intersection. Again what is Q implies P? Negation Q union P. Negation Q union P. So negation of. So here I got combinations of two principles. That is two prepositions. Negation P union Q intersection negation Q union P. Now here I am applying the distributive property, left distributive law. A intersection B union C formula. In the place of A, I am assuming here A equal to first preposition negation P union Q. In the place of B, I am assuming B equal to negation Q. In the place of C, I am taking P equal to C equal to P. Okay. Left distributive principle for this quantity. So A intersection B union C. What is A intersection B union C principle? A intersection B union A intersection C. Okay. A intersection B union A intersection C. So A intersection B means what is A here? Negation P union Q. Intersection B means negation Q. Union again A intersection C. A means negation P union Q. Intersection C means P. This is distributive property. After writing the distributive property, the above equivalence relation can be converted to like this. Next, negation of. Again here we have negation P union Q intersection negation Q. So take associative property, negation P union Q intersection negation Q union. There also associative principle, negation P union Q intersection P. Next. Next year. What about result? 1 minute. So it will become negation of negation P union Q is here. This step. Negation of negation P intersection negation Q union Q intersection negation Q. So it will become here this I'm writing negation P union Q intersection negation Q, negation P union Q intersection P. So in this here I am taking negation P union Q common quantity. So this is a negation of negation P intersection Q union Q intersection negation Q union negation P intersection P union Q intersection P. Okay. So this is negation P and Q, negation P intersection Q union Q intersection negation Q, and here uh, negation P intersection P union Q intersection P. So it will become negation of P union Q. What is Q intersection negation Q? It is always true only. True with union negation P intersection negation P also true value. True union of Q intersection P. So finally we'll get negation of negation P and Q union Q intersection P, because P union Q union T always equal to P value only. But in the place of P we have P union Q. And Q intersection P with union of T will become again same that preposition Q intersection P. So finally it is equivalent to P union Q intersection P intersection negation P intersection Q. These are the few results. Okay. Similarly, next coming to the next topic is duality law. Okay, this is not required. Okay, next tautology implications. Of course, this also we finished. Here, yes, I will explain one problem in both cases. Okay, just now we finished all the problems without truth tables. Let me take one example with two tables and without two tables. I want to get the same result. Let me do one example here. So these are the first, remember the principles, tautological implications, definition. A statement A is said to be tautologically implication with a statement B if and only if the condition is A implies B, that is A conditional B is always tautology. For this, come to the principles, formulas. These are also important formulas. P intersection Q implies P. P intersection Q implies Q. P implies P union Q. Negation P implies P implies Q. Q equal to P implies Q. Negation of P implies Q equal to P. Negation of P implies Q equal to negation Q. And P intersection P implies Q is always equal to Q. Negation Q intersection P implies Q equal to negation P. Negation P intersection P union Q equal to Q. P implies Q intersection Q implies R equal to P implies R. Last one, of course, in few problems, we may use these principles. P union Q intersection P implies R intersection Q implies R is always equal to R preposition R. Okay, let me do one example with truth and without truth tables. What is our question? Show that P intersection Q equal to P is always a tautology. Means we will get all values must be true only. First, let me do this problem without constructing truth table. So P intersection Q implies P. So this is equal to negation P intersection Q union P. So it is in the form of like this. P implies Q. What is P implies Q? What is P implies Q formula? Negation P union Q. But in the place of P, I have P intersection Q. In the place of Q, I have P value only. So P implies Q means negation P. Negation P means negation of P intersection Q. Union Q. In the place of Q, we have second function is P. So that is formula will become like this. Negation of P intersection Q union P. Again, apply the De Morgan properties for negation of P intersection Q. So what is A intersection B whole complement? If you apply the same principle in set theory, A intersection B whole complement, it will become A complement union B complement. Same I am using here also, but in the place of A I have P, preposition P. In the place of B I have preposition Q. So negation of P union, sorry, P intersection Q will become negation of P union negation of Q. Union outside we have another preposition P. So negation of P union P. Just I am going to apply the associative property. A union B union of C. First write Q union P, negation Q union P, P union negation Q. Then afterwards apply the associative property. We will get finally negation P union negation P union of negation Q. What is negation P union negation union P with union P? That is always true only. So negation P union negation Q, it is equal to true. Union of negation Q. Okay. What is true function with any preposition? Answer is always true. So finally I got it is tautology. Same this result I can use by what do you call, by uh, truth tables. So here how many statements we have? Two, P and Q. So write P and Q means combinations like this: TT, TF, FT, FF. Next, what is asking? P intersection Q. We need to find P intersection Q. What is P intersection Q? Yes, P intersection means this is the result will goes to true whenever both statements are true. Remaining all three cases, it is always false. So P intersection Q will become TT, it is T, TF, it is false, FT, it is false, FF means it is false. This is P intersection Q. Next, P intersection Q implies P. P intersection Q implies P. So P intersection Q means use this column, third column with first column. T to T, it is always T. F to T, it is always T. If both are false, it is always T. Both are false, it is always T. So this is the having this last column P intersection Q implies P, having all T's means all truths, means it is an example of tautology. So I proved this result in both cases. With construction of truth table also I got a T. Without construction truth table also I got T. Okay. Sometimes they will have the question like this: prove without truth tables or prove with two tables, or check the answer is same or not with and without two tables. Means we need to do in both cases. Let me take one more. As functional, okay, converts, connectivities, okay, these are not required, okay, choose. Let me do. So again, here we have some more formulas here. P union Q is always equivalence to, let's remember these principles. P union Q is always equal to negation of negation P intersection negation. What this is a distributive property. Negation of P intersection negation Q. If I apply the negation for this, it will become P union Q. P intersection Q also same. And P implies Q formula is, yes, we used this formula for proving all previous problems. So P implies Q equal to negation P union Q. And double implies, yes, remember this. Double implies formula. P double implies Q or P biconditional Q equal to P intersection Q union negation P intersection negation Q. This is one formula. Or else P double implies Q equal to, yes, these last ones here. I written three different formulas for P double implies Q. What is first one? P double implies Q. It is always equivalence to P intersection Q union negation P intersection negation Q. Or you can apply one more formula for this one. P implies Q, it is equivalent to P implies Q intersection Q implies P. As with the help of this second result only, I proved 2-3 problems in uh, previous examples. Next, same this P double implies Q is always equal to negation P union Q intersection P union negation Q. Okay, all these are the equivalence conditions. You may write P double implies Q equal to combination of P double implies Q equal to either of these three formulas. Okay. So in this here, the set of connectivities, up negation or intersection, negation or union, are minimal frequencies complete set. Next, sir, uh, derived combinations. Okay, this is not NAR. Okay, let me check out in our textbook. What about the next quantities? Just I will share your textbook. Sir, okay, before going to textbook, just see NAND and NOR gates. NAND and NOR gates. These are the special connectivities. Yes, day before yesterday we discussed negation, conjunction, disjunction, conditional, biconditional. Okay, these are the NOR and NAND. Means quite opposite of and that is intersection conjunction table, and quite opposite of or means disjunction table. So here NAND, coming to the first NAND, it means negative negation of conjunction of the true statements. It is denoted by up arrow mark, and its truth table will be like this. P comma Q, I am taking two prepositions. So if we apply the P NAND Q, we can read this upper arrow mark is P NAND Q. So this is quite opposite of, I'll show it, AND table. Where it is AND? And what about AND table? If both are true, then only the P and Q will goes to true. Remaining three cases, it is false only. So that is AND table. But what is NAND? It is quite opposite of AND. In AND, we have only one true value whenever both are true. Remaining three situations, it is false only. But whereas NAND, only one case is false. Remaining three cases, it should be true. Am I right? See here. P, Q, two statements. P, T and QT. Answer is false. Why? Because it is quite opposite of AND gate. And that is conjunction truth table. So TF means there we will get false, but here we will get the T. Remaining three cases false, but here remaining three cases shows true. TT, TF, FT, FF. It is F, remaining three cases true, true, true only. Next, NOR gate. NOR special connectivity. It is the quite opposite of OR, that is disjunction. It means negation of disjunction of two statements. It is denoted by down arrow mark for the given tables here. Uh, Again, coming to the truth table for this. So NOR. NOR means it is quite opposite of R. What is R truth table? That is disjunction truth table. If any one of the preposition is true, then the result is true. In both cases, it is true, the result is true. Only one case it will be false. That is, if the first preposition, second preposition will goes to false statement, then only the disjunction will goes to false. Otherwise means remaining three cases it is always true only. But whereas in a NOR gate, NOR special symbols, remaining one case it is true and all three cases false because it is a quite opposite of OR gate. So here PQs are TT, TF, FT, FF. Then P nor Q, P nor Q will become both T, it should be false. If any one of the false, then it will goes to true. Both are false, it is goes to true only. So this is a truth table. Uh, FF, okay. In OR gate, we have three true values, one false condition. Whereas NOR gate, we will get three false, one true statement only. This is about NAND and NOR gate. Just next, what about next topics? Fundamental gates, XOR, exclusively OR. Okay, exclusively OR here. I will explain this one also. Assume P and Q are two prepositions, then the exclusion or XOR of P and Q denoted by double notation P exclusive of Q, that is plus with circle. P exclusive R is the preposition that is true when exactly one of P and Q is true, but not both it is false. Otherwise, it is and it is false. Otherwise, means any one of the quantity is true, the result is true, and it is false. Otherwise, means both are false. It will go to false. Coming to the truth table, yes, TT, it is false. TFT, FTT. So what is OR table? OR table, it is quite opposite. Okay, TT, it is false. Both T, the result is false. Both false, the result is false. If any one of the preposition is true, then resultant uh, preposition P or XOR preposition Q, it will become true. Okay, these are the few principles. And next class I will going to explain the normal forms. Okay, this is also important topic for your final exam. Okay, next class we will discuss the normal forms. So whatever the topics we discussed today, please practice all that. And in your textbook also we have similar examples. Just I will show it. 1 minute, I will close the class. One minute. Okay. Yes, we finished it today. Half of the part of unit 2. We have one more little bit topic, that is normal forms. We will discuss that normal forms in next class. Sir, all these problems today we covered. Explain these problems here. Just practice this one. Okay, in your textbook they given with solutions also. Please do practice this. Show that the equivalence relation is page number 18, page number 19. Yes, table also same that's here. Okay, next class we're going to start the normal forms. Okay, next disjunctive and conjunctive normal forms. We'll discuss these topics in next class. Okay, I'm going to stop. Let us continue next class. Right.